Space is huge, immense beyond our wildest dreams. In order to explore and settle it, we'll need to learn to dream a lot bigger and bolder than ever before. Welcome to Science and Futurism with Isaac Arthur, and I am your aforementioned host, Isaac Arthur. And I've been writing and producing this show for almost 10 years now, and spent a lot of time talking about space settlement. So much so that I was elected president of the National Space Society last year and received the Pioneer Award from the International Space Development Conference a few years before that. During that time, between chatting with this audience of space enthusiasts and all the folks from those organizations and events, I've encountered even more excellent ideas about how to settle space. And I felt like it was time to try to summarize our discussion of interstellar colonization into something thorough but concise. For channel regulars, they know that my definition of concise is from the same dictionary Peter Jackson or Zack Snyder presumably use, so they are already grabbing a drink and a snack. If you're new here, feel free to pause and go grab some yourself, because we're going to be here for a bit. Even as long as this episode is though, it will often only skim the surface of topics, and we often have entire episodes, usually more in the half-hour long range, that deep dive into many of these topics more, and I'll mention them as we go along. Feel free to pause and watch one of those, or check them out when this episode is over. Unlike some of our other compendium episodes, this one's meant to be watched more from start to finish, at least the first time round, as it's sorted more by approach and concept than alphabetically. But you can still skip around to the parts you want, and I'll give a quick overview and put the table of contents up momentarily. Way back at the end of the first season of this show, I did an episode called Interstellar Colonization, and over the years we discussed it probably more than any other individual topic on the show. And as this show approached its 10th anniversary in 2 more months, it seemed like a good time for a more extended look at the topic of interstellar settlement or colonization, such as we've done for megastructures, advanced spaceship drives, and the Fermi paradox in the last couple of years, and we'll probably do for terraforming techniques next year. We have a lot to cover, so without further ado, let's jump into our list of topics. And don't forget to hit those like and subscribe buttons, or join the channel, or jump over to our Patreon page or website, isaacarthur.net, if you want to support more episodes like this.
Table of Contents.
We have 5 primary categories to cover today, starting with the motivations and goals of space colonization. These are things like exploring or gaining resources or protecting humanity in the long term. Our second main category will be a quick overview of the various types of spaceship drives we most commonly discuss in interstellar travel and what they can do and how they work, such as ion drives or the Orion Drive, or those running on fusion or black holes, or alternate approaches like beaming systems, solar sails, or mag sails. After that, we'll move into actual ship types, as defined by mission and ability, from FTL ships and generation ships to sleeper ships, von Neumann probes, seed ships, giant planet or star-sized ships, and various hybrids in between, as well as a discussion of ship shapes and avoiding collisions, and their purposes like collecting resources. Then we'll move on to colonization strategies, covering concepts like lowest hanging fruits, prime versus subprime planets, percolation theory, backfilling, colonizing, garden or cones, collector fleets, and even multiverse colonization strategies. Then we'll close with our last category, giving a quick overview of the challenges and methods for early settlement of a new system, from picking planets to possible fatal problems like the Aurora Effect, or uninvited guests in the form of new colonists seeking to share or steal your claim. A basic overview of the terraforming challenge and what needs to be done to let a colony send out its own colony ships, proving that interstellar colonization is truly desirable and sustainable galaxy-wide.
Motivations.
We have a lot to cover today in order to talk about how interstellar colonization can be made to happen, and we'll barely scratch the surface. But to begin that journey, we need to first understand the motives and goals and means of making it happen. Those include reasons like exploration to see and visit new places, population growth to find room for more folks who can build new civilizations, to acquire the resources to do that and other projects, to achieve long-term safety for humanity, not keeping all our eggs in one basket, to escape enemies, be it tyrants, or AI, or alien invaders, who might seek to oppress, enslave, or annihilate us. We'll finish this section with a discussion of how we might fund these efforts, and if interstellar private, for-profit investment can ever be a sane option and alternative to government funding or donations by motivated groups. We should also note that you can have multiple waves of settlement with different motivations. For instance, we use settlement and colonization fairly interchangeably in our discussions of space because we assume we're going to lifeless planets no animal, let alone intelligent creature, has ever claimed. So the nastier connotations associated with the term colonize don't typically apply. But a civilization might settle a star system, then have future waves arriving from Earth or another star system that might be bent on peaceful interaction or outright conquest. We'll explore that more in our upcoming episode Life as a Planetary Governor. Our focus today, though, is more on that first wave of settlement and what precedes it, like exploration.
Exploration?
Humanity has long tended to boldly go where no one has gone before, and for many that is motivation enough for going to space. I don't disagree, though we'll cover several other good motivations in a moment, and this one can get exaggerated by our experience with science fiction. In good space opera, every week the crew meets a new civilization, or strange and mysterious phenomena, or finds some new super technology or rare element that exists nowhere else. Now, once humanity has colonized the galaxy, there will be strange new civilizations everywhere. There'll just be those descended from us or made by us, all natural and adopted children, and probably some horrible mistakes like murderous AI. Nothing about what we've learned in regard to the universe in the last century has indicated that there's a lot of uniqueness out there in a scientific context, and while there may be plenty of alien life in our galaxy, it doesn't seem to be flush with other civilizations. And what we know of physics says to reach one will probably take thousands of years, and the same to reach the next one, not a week or two, even if the galaxy has thousands of extant civilizations to visit. This does not mean there isn't plenty to explore, but it's likely to be a lot slower and less flashy than we expect from sci-fi, at least until we grow to the sorts of massive populations we envision on the Kardashev scale. And while that would be exploring ourselves, think about all there is to explore on our planet and our diverse civilizations, past and present, and imagine that scaled up 1 billion-fold, and know that an explorer in the future will never run out of new and interesting places and people to visit.
Population growth?
Population rates rise and fall as technology and cultural change. We grew enormously in the 19th and 20th century, and have added 2 billion more humans to the net total since the 21st century began, but many trends suggest we may be seeing a slowdown in growth. This may remain, or it may not, but I tend to be of the opinion that any civilization that can comfortably grow will tend to do so over time. We feared a Malthusian catastrophe the last couple of centuries, where our numbers grow beyond our ability to support them and civilization collapses on itself, and I think it's gotten into our culture and encouraged us towards smaller families, among other factors. Perhaps in 40 years, those countries who have had populations stagnate or decline will fear collapse from that and see a cultural shift to bigger families. I tend not to trust population growth estimates because they tend to oversimplify and have a pretty good track record of being terribly wrong. But more importantly, I tend to assume that the biggest two factors in population growth reduction in the developed nations is ready access to birth control and our tendency to encourage folks to start families later. We see improvements to fertility treatments too, and that's likely to have the opposite effect, but I doubt it's a zero-sum game. More importantly, if lifespans keep rising from technology and fertility methods keep improving, folks won't be choosing between education and career versus starting a family early. And I think you'd see a rise in births from that, while also seeing decrease in death rates as folks lived longer. To me, this mostly indicates that civilizations can adjust their population trends to meet perceived needs and limits, albeit it can be slow and temperamental to throttle. To others, it spells inevitable population collapse or Malthusian catastrophe. Time will tell who is right on that, but it is traditionally a big motivation for space colonization, and not a bad one. New lands for more people. You build towards what we usually call a K2 or Kardashev 2 civilization, one that uses all the light its sun emits for running its civilization. K1 civilizations are those that use all the sunlight heating their planet, and K3 are the power of their whole galaxy. Unofficially, K4 would take that to the supercluster scale, and K5 to the observable universe. K1 is around 10 to the 17 watts, a few orders of magnitude greater than what the human population currently uses, unless you include agriculture in that, and in practice we don't really mean 100% usage, but rather a significant percentage, potentially up to 100%. Same for K2 and beyond. Technically, it's just a big enough percent of that whole power figure to let such a civilization be astronomically detectable for making their planet or star system or galaxy have a power emission that's visibly off to astronomers, as it originated as an approach to astronomical SETI, the search for extraterrestrial life. It's not a measure of population, technology, or enlightenment, just visibility, but it gets used to discuss those others a lot. See our Kardashev scale episode for more discussion of that and the capabilities of those civilizations. K2, though, is a billion times greater than K1 in power output, and all things being equal implies a billion times as many people. It's a similar jump to K3, K4, and K5. To become K2, you build up space habitats on every asteroid and moon, and scrap others to build huge power collectors and more artificial habitats, like O'Neill cylinders, and there are more options like starlifting for coming up with more raw materials from your local star system. We'll discuss accessing the sheer raw materials and resources for building to K2 levels in a moment, but it means we have lots of places to put a growing population in this solar system and plenty of energy to get them to space, so again, a good motivation for space settlement. But it doesn't work as well for interstellar colonization. We'll discuss some practical ways for moving lots of people to other star systems today, but in most cases it takes less energy to build a space habitat for some folks that's fairly lavish by modern standards, and to support them for many thousands of years, than to take those same folks to another star system, even a neighboring one, in less than a normal lifetime. And during that journey, if you're not controlling your growth back home, you will have spawned more people back home than you shipped out. We explored the more extreme limitations on human population levels on lower energy in last week's Cyborg Civilizations episode. Interstellar colonization is a great way to add more people to the total human race or descendant clades, and in-system colonization is a great way to accommodate more locally, but neither lets you grow your population infinitely. Even multiverse colonization probably doesn't let you do that, so whether it's 10 billion humans or 10 billion quintillion, there's a limit somewhere. I would still say bigger is better though, more lives to live, stories to tell, families and friends to dwell, and the empty rocks and stars are just slowly burning away uselessly to entropy if we don't grab them and use them. Though thankfully, there are a lot of them and not too much of a rush to get to them.
Resources.
Space is enormous, and most of everything is in it. Earth actually has roughly as much material in it as all the other rocky planets, moons, and asteroids in our solar system combined, most of the remainder being in Venus. But Earth is still tiny compared to any of the gas giants. And Jupiter has the same mass and materials as every other planet, moon, and asteroid combined. And yet, the Sun has even more. 99.8% of the mass in our solar system is the Sun. Jupiter makes up half the remainder, 0.1%, and the other thousandth is spread around, but mostly in Saturn. It's a lot of resources, especially considering we've barely just scratched what is in Earth's thin crust, let alone the mantle and core. And yet the galaxy has 1.5 trillion times the mass of our solar system, and only a small fraction of that is in the other stars. It is almost impossible to imagine how you could possibly even dent that total, and it's all out there waiting for us. There may be other civilizations out there to claim a stake, though I doubt there are any in our galaxy. Indeed, we probably have several galaxies to ourselves, out of the many billions of galaxies we can see, and possibly more beyond the observable universe. But even if we had to share the galaxy with 100 other civilizations, it would mean quadrillions of times the resources Earth has were still ours to claim as our share. Riches and resources to run civilizations that are far more immense and prosperous than anything before, and that seems like motivation enough. But to claim it, we'll have to go get it.
Long-term safety.
Don't keep all your eggs in one basket, the saying goes, and it's not wrong. This is an example of a motivation that doesn't really need to be true to work though, since we simply need to believe settling other stars makes humanity safer to pursue colonization under this motivation. In truth, more star systems isn't really making you much safer. There's really no natural disaster that's going to kill off an entire star system, especially when large chunks of the population might live 100 miles down inside some asteroid. When it comes to the unnatural kind, however, like alien invaders, or rogue AI or tyrannical governments, they are going to be able to follow you to your colony planets. Those colonies also become a possible threat to you themselves, as we discussed back in the Chronos scenarios. That said, the basic idea that we need to settle other worlds so we're not wiped out if this one perishes is certainly still valid. And more worlds means more minds and muscle to handle problems facing humanity too. But the concept of colonization to protect humanity from extinction gets tossed around a bit like a jingo and shouldn't be overestimated in its real utility. It helps, but we could probably survive till the sun burned out without another planet, and the only real danger to us is other humans or human equivalents like AI, and that's a threat we export to every planet we go to.
Escape?
Running away from a broken planet or an alien invasion is popular in science fiction, but as motivations go, this certainly sounds good, but in practice probably is not going to work. Terraforming a planet to be livable is hard work, and harder when doing it with whatever people and gear you brought on a ship. You could nuke Earth till it glowed in the dark and most of the seas and sky vaporized off into space, and you would still have an easier time terraforming it than Mars, even if all you had to work with was the handful of remaining mutant cannibals living in underground bunker fortresses left over from Armageddon, and running around with half-broken and barely jury-rigged technology. This is how hard terraforming is, and how absurd the idea is of wrecking Earth and fleeing to some virgin planet to try again. Mars makes Antarctica or the Sahara look like paradise, and Venus is a suburb of hell. And those are our two best terraforming targets in the known universe. I'm sure there are other better Earth analogs out there, and we'll probably start finding them this decade, but Earth analog is an ambiguous term, and all of those are, at a minimum, hundreds of trillions of miles away. As to alien invasions, you can flee an enemy if you've got something approaching technological parity with them, and you might well have it if you're already an interstellar civilization with systems dozens or hundreds of light years away that they had to invade you through. You could be watching and learning as they came, and put up a big fight at your homeworld, and let your colonies in the other direction flee as fast as they can for distant regions of the galaxy, all with centuries of prep time. An attempted 3D spherical enclosure around you in the first place to block all exits is unlikely to ever be deemed viable, let alone practical, at the interstellar scale, so some colonies will be able to get advanced warning to flee. On one lone planet, even assuming you even got advanced warning to do something, any ships you send running from your homeworld that don't get blown out of the sky instantly will just be overrun by the picket ships they sent out around the system and never bothered decelerating when the rest of the fleet did, as they were dispatched to deal with that contingency because your alien invaders who can build enormous space battleships are not idiots. We did examine this scenario in more detail in our episode Extragalactic Sanctuaries, and that chronicles a battle across several million planets and years, and the extreme efforts needed to successfully escape someone bent on their destruction. As an upside, if your desire to escape is a bit less severe, say a political or religious group wanting to flee all civilization, then they might have this as their motive and be able to do it just fine. Given the sheer enormity of interplanetary space, fleeing to other stars seems overkill, but they may feel it necessary. Assuming they can pay to build those ships, then even flight across the galaxy to another one isn't off the table, and this is certainly a plausible motive.
Funding and investment.
One of the big questions for building an interstellar spaceship and colonizing distant planets is who the heck is paying for all of it and why. We just listed some motivations that might encourage folks to cough up money or volunteer their time to help, or volunteer a lot more time to voyage on these missions. Big projects often do attract big interest, and big funding, often via donations. Also, as we already noted, as a civilization expands inside its original solar system, the amount of effort it needs to make a colony effort work remains the same, while its total capacity rises immensely. So the Alpha Centauri equivalent of the Apollo mission might take 1,000 times the resources to make happen, but a highly automated society might be able to offer those, and if not, as it grows its way up the Kardashev scale, the mix of more people and more technology is going to get you there. That said, we shouldn't ignore classic investment. It works if we ever get FTL working, but also can work with our options inside known science. We don't know what sort of economy we will use in a few hundred years, but the basic principles of investment will probably tend to apply in whole or part still. One of those is that while it would make sense to invest in something that is likely to pay you back double, it wouldn't make much sense to make the investment if the return is coming in 100 years, because even a savings account that only gets you 1% growth a year is going to be worth 2.7 times the value in a century, and that's a fairly bad return even compared to something like government bonds, which are probably more reliable than stock in an interstellar colony. Now, I think we are in for longer lifetimes in the future, and that does encourage longer views on investment, but whether you're living to 1,000 or not, you still don't bother with investment with that lower rate of return unless you just want to support the cause as some quasi-charity, which is also common enough and should not be discounted. But with longer lives also probably comes extended good health and changing ideas on retirement, which is mostly a 20th century concept anyway. When Social Security started, the majority of people didn't live to collect it. The retirement age was 65 and the average lifespan was 63. Our interest rates are very tied to funding pensions and retirement these days. If a person is not really aging and just gaining new skills, knowledge, contacts, and influence as time rolls by, they really don't need to be working as hard to save up money for when they're in mental or physical decline, but they also have a way easier time building savings up. That would generally tend to indicate lower interest rates because there's less urgency to borrow and a bigger supply to borrow from. If the local economy isn't a huge growth boom, then you have plenty of new wealth and prosperity to provide charitable or government funding for colony missions. If not, the interest rates are probably low and make investment at lower rates of return more viable. But a colony mission doesn't need to be a low rate of return. Let's imagine we had an investment offer for a colony that thought they could build their Ark ship, launch it, arrive, develop, and ship things back to Earth 500 years from now. I imagine the investment is in fiat currency, but let's phrase it as a commodity currency for the moment. We have to invest 2 gigatons of construction material to build the ship, and some much larger but mostly irrelevant quantity of hydrogen and deuterium to run its fusion reactors. Let's say in commodity terms it was going to be a total cost of 10 gigatons of that material to send the mission. Our analysts say it's about a 50-50 chance the mission will succeed, so we tell them to agree to 20 gigatons of return, with 500 years of interest at say 2% per year, for us to consider that a good investment. 2% compounding for 500 years is 20,000 times the original sum, incidentally, so they need to send us back 400,000 gigatons of metal to us to make it profitable. They are probably doing this over many decades, but regardless, as huge as that is, 20,000 times what was invested, it's not even the total metal in just one larger metallic asteroid. Our own asteroid belt contains around 1 million asteroids, most much smaller than that, but that belt is not even 1,000th the mass of Earth, let alone the total resources of this solar system. So our solar system can spare it, and odds are so can theirs, many times over, and it's a trivial cost compared to the immense gains involved. Now, that was obviously oversimplified, but the concept holds, and moreover, I do not need to expect to be alive in 500 years to collect on that. I have bought stock, say they issued 10 billion shares, the equivalent of 1 ton of material invested each, and if all goes well in 500 years, each of those shares will yield 40,000 tons. Well, 10 years down the road, the ship is successfully built and ready to launch, and analysts move the success odds up from 50% to 60%, because a lot of these missions fail to ever make it to launch. We're also now only 490 years out from the payoff. So I can sell my 1 ton stock, eventually good for 40,000 tons, to someone else who who might now view it as worth, say, 1.4 tons. 10 more years down the road, when all is still going well, and they turn off the drives to coast for the next century, the success odds might move up to 70%, and we might say the share's value has moved up to 2.1 tons on the market, just over doubling after 20 years. And in this case, it might be a good time to sell some of that stock now that a lot of the risk has left and we're about to be left with a big long wait. But every year it's going to rise in real value as the time to payoff diminishes and the various risks diminish if all goes well. This is simply an example and an intentionally simplified one. I am neither an economist nor a finance guru. It's merely a demonstration of how someone could plausibly and sanely invest in something not expected to mature for half a millennia. It also illustrates why faster ships, even with exponentially higher fuels or energy budgets, might be preferred for colonization, and also why some of our colonization strategies we'll discuss later, like aiming for the nearest empty system, not the nicest Earth analog system, might be plausible, or why some very slow-crawl colonization effort passing through the Oort cloud and oozing out into the galaxy at less than 1% light speed might still work, or even work when you can do it faster but still stop to grab every rock in the interstellar void along the way. In all cases, the faster you can get there, often the better the outcome, even if you have to throw a huge amount of energy and hydrogen at it. Of course, you can only go as fast as your spaceship drive will let you go, and your spaceship can go at without being smashed to bits.
Spaceship Drives.
We'll be covering types of colony spaceships in a moment, but this has more to do with their purpose than how they move from star to star. We have an entire 2-hour episode dedicated to this topic, the Advanced Spaceship Drive Compendium, so we'll be keeping the topic brief today, but a few deserve a special note or summary because we'll reference them a lot today. There are dozens of major drive types, from those solidly inside known physics or already in use, to those that would seem to blatantly violate energy conservation or special relativity. These can include wormholes, warp drives, and other FTL systems we've given their own episodes, or options like differential or gravity drives that operate without the need of propellant. We never want to rule out what the future might give us, but most serious conversation about interstellar spaceships focuses on a few key systems and a few key concepts. One of those is that as long as you're using an onboard propellant, you are under the tyranny of the rocket equation, and can only go a few times faster than however fast your propellant comes out the back of your ship. It is increasingly hard to go beyond that exhaust velocity, and 2 or even 3 times that speed comes at sacrificing virtually all your mass to propellant or fuel. There is no technical limit on how fast an individual propellant can push a ship though, it simply exponentially rises until the point of absurdity. As an example, to go twice the speed of your exhaust, you need 7.4 times more propellant than ship and cargo. To get to thrice the speed, 20 times the propellant to ship and cargo. 4 times the speed, 54.6 times the propellant. 5 times the speed, 148 times the propellant. This starts pressing the ability of practical engineering too, as all that fuel needed something to contain it in, which had mass too, something multi-stage rockets can't help with in part, or being able to recycle that rocket propellant container to use as propellant itself. To achieve 10 times your propellant's exhaust velocity takes 20,000 times as much of it as you've got ship, cargo, and fuel tank. I don't think you could build a ship able to achieve this, and if so, just barely, and it wouldn't carry much cargo, which is rather necessary for a colony mission, though nanobot self-replicators are one colonization strategy that can plausibly consider such high ratios. Worse, in space, nothing is there to stop you, so if you want to slow down using propellant at your destination, your final speed is essentially halved. Doubling your speed though takes far more than doubling your fuel or fuel ratio. Chemical rockets have exhaust velocities of thousands of meters per second, while the best propellant, photons of light, or presumably gravitons or near-massless neutrinos, are your best at a few hundred million meters per second. Another key concept, unsurprisingly then, is to get your slowdown at the destination in whole or part by local sourcing. This can include magnetic or even physical sails dragging on the local interstellar medium, and drag in space even before relativity kicks in, goes with the third power of your velocity, as if your speed is 10 times higher, you hit particles in space 10 times more frequently, and each carries 10 squared, or 100 times the kinetic energy relative to you, thus exerting a drag force 1,000 times higher. Thus, such slowdown sails, while still costing you mass, might help you slow down more easily at high speed and let you use other methods, including fuel, to slow down easier from that lower speed. So the key concept here is to slow down, or speed up, wherever possible without using onboard fuel. This hints at another key concept of space travel, which is that all your equipment has mass, and mass takes more energy to move along. So not only do you want to be sparing with it, you want to be able to use it for more than one thing. This is why we often won't use multiple drives in tandem even when they might work better, one for a lower speed and one for a higher one, or maybe in an atmosphere, because the actual equipment for doing it just masses too much and requires too much maintenance and operation, which requires the additional mass of a toolbox, spare parts, and an engineer. Bigger ships often have an advantage here in that they can afford to carry a wider array of options, and redundant bits don't cost as much mass, nor do they need as high a percentage of radiation and collision shielding. But things like a magnetic sail can serve as forward shielding while wrapped up during the voyage, and then be extended to slow down, or a pusher plate for an Orion Drive might be recycled into forward shielding once the initial acceleration was done, and then recycled again into a mag sail, then once more into a pusher plate and radiation shield for the remaining slowdown, then maybe even one more time into a space elevator for the destination planet, or big power collectors for running manufacturing, life support, or an ion drive in system. Key concept again, interstellar voyages are very long, and if they have a live and awake crew, they need activities to do. Stages of voyages might be decades long and permit year-long processes in between for switching and changing things, unlike modern spaceflight.
Ion Drive.
Another of those concepts, which is strongly in play with ion drives, is that you can achieve much higher velocities by slower accelerations over very protracted timelines. This is useless for getting off a planet. Even many minor planets with gravity so weak you could jump off them might be too much for such drives, but they can be run for a very long time on a power supply and shoot ions out the back at much higher speeds than traditional rocket propellant, typically by electric or magnetic fields, which accelerate them, no different than the vacuum tubes in older TVs. This means you get far more speed out of the same amount of propellant and, if patient, can achieve far higher final speeds. They are generally thought to be better than chemical rockets for interplanetary missions, as they have more time for their slow accelerations, but it is really at the interstellar scale they can shine. Higher powered ones in the megawatt range or greater, and on vessels where crews can perform maintenance on the electrodes, are thought to be able to exceed 1,000 kilometers per second, 0.33% of light speed, and possibly considerably higher, so long as they have time, which is rarely in short supply on interstellar voyages, a good power supply, like a fission or fusion reactor, and solid maintenance. This is one example of an engine type well inside known physics and engineering that makes it into the interstellar capable category, though barely, and is usually assumed most more powerful fusion and fission drives are operating as the power source of a stronger ion drive.
Orion Drive.
One exception to that is a nuclear drive powered by detonating bombs out the back behind the ship, the most well-known version of which is the Orion Drive, and this ship should have no problem achieving 1% of light speed and possibly as high as 5% of light speed, though I tend to suspect it would end up somewhere in the middle. There are many versions of these types of post-nuclear systems. Daedalus is another well-known variant, and there is also Medusa, which essentially uses a reverse parachute, one extended forward of the ship which bombs are detonated inside, pulling the chute and dragging the ship behind it. In most cases, we assume the magazine contains smaller fission bombs, but very large Orion drives, such as those an O'Neill cylinder-sized generation ship might use, could potentially use high-yield fusion devices, which would achieve a higher final speed as larger fusion devices have a higher energy-to-mass yield.
Fusion Drive.
Fusion-based drives are attractive based on two core characteristics. The first is that while a plutonium or uranium atom undergoing fission usually releases 10 times as much energy as hydrogen or deuterium fusing, they also mass on an order of 100 times as much. So fusion is about an order of magnitude more energy dense as a fuel than fission. The second is that fusion is of lighter and very common elements, while fission uses heavier and rarer elements. Thus, fusion represents an energy supply an order of magnitude denser than fission, and many orders of magnitude more abundant as a fuel. Ideally, they would have no great problem achieving 10% of light speed, or maybe even a bit higher, but the problem is releasing that energy. If you're converting it to electricity, you can run an ion drive with some losses, and are then limited by how fast you can shoot ions out the back. There's that critical exhaust velocity again. There is no limit on how fast an ion can move. Our sun's core generally moves around at about 2% of light speed, but this is actually way colder and slower than a real fusion reactor would need. Since our sun takes billions of years to use its fuel, and we probably would like something able to burn it in years or decades, faster than even the hottest supergiant core, though not quite at supernova rates. Until you get truly relativistic speeds, 100 times the energy means 10 times the speed, and energy runs linear to temperature. So a stellar core at 100 times hotter than our sun, and the biggest hottest ones achieve this, would be expected to have atoms moving 20% of light speed instead of 2%. And that really is the practical upper end of fusion drives, simply from energy constraints of how much energy the fusion events release. I would not expect to achieve that without new science either. We usually envision this with what's called a fusion torch drive, where the reaction occurs and all blows out the back like a rocket flame. Achieving this with practical engineering is kind of dubious, and a variant of this, the classic torch drive suggested by Robert Heinlein, where the name comes from, is more like a pure matter-to-energy converter, and presumably spits photons or neutrinos or some other light-speed or near-light-speed particle out. Neutrinos are nice since they don't interact with anything, and thus don't melt your rocket or the planet you're pushing away from. Same for a hypothetical dark matter propellant drive.
Black Hole Drive.
Black hole drives are a nice option in that they achieve the Heinlein torch drive profile and mostly spit out photons, at least if our notions of Hawking radiation turn out true, and if micro black holes can be made. See our recent episode Kugelblitz Black Holes for more discussion of that, but whether it's a small one or a big natural one, it can be turned into a powerful spaceship engine more efficient than any fusion reactor. Albeit for natural ones, it is a spaceship drive massing 3 or more times as much as our sun. In the absence of micro black holes, ships of this scale are used principally in planet ship designs for crossing entire galaxies or between them, and function by dumping matter down that black hole's gravity well, which releases large amounts of energy at an energy-to-mass ratio of an order of magnitude higher than fusion and 2 orders over fission. It's a very large but also low-tech approach, which I know sounds hilarious as we tend to think of black hole technologies as hyper-advanced, but it's the technological equivalent of throwing junk down a giant hole and using the energy that erupts out of it as a result. As such, it's an approach that works to a lesser degree and in a different way on any dead star, such as white dwarfs or neutron stars. Living stars, as discussed in our episode Fleet of Stars, can also be turned into spaceship drives. Indeed, several variations are possible, with the Chicago thruster being the easiest and best known, but also rather slow to accelerate compared to other options.
Beaming Systems.
The other way to turn a star into a spaceship drive, and without moving it either, is simply to tap its energy to power beams of light, or microwaves, or particle beams to push a distant ship. The simplest approach is the stellaser, which drops a pair of large mirrors into a star's corona and uses the plasma there as its lasing medium. Simple solar-powered lasers or particle accelerators work too, and they may also be powered by a fission or fusion reactor at some deep space outpost. Such beaming arrays can push a ship arbitrarily close to light speed. A relay system between 2 stars might also keep a corridor heavily monitored and clear of debris and allow faster and safer travel between developed star systems. Higher speeds are possible at the intergalactic scale too, as it's much emptier out there. A ship leaves the system and is pushed up to speed by a beaming array, then slowed by the systems array on arrival. Hybrid systems would also be probable, such as a beaming system of particles that the ship could absorb and be pushed by at slower speeds, and which at medium speeds it could use an energy beam to heat those particles or use them in an ion drive powered by the beam, then switch to reflecting the energy beam backwards at higher speeds. You get double the shove by reflecting a beam rather than absorbing it, and can bounce it in a different direction to change the angle of push. Such beaming systems can also get not just energy to run a ship to it, but also raw materials, as a pushing beam might be composed of useful atoms like carbon or oxygen or iron that the crew might need to replenish lost reserves. While this is usually seen as a means of making interstellar travel and trade easier for developed systems, moving goods or travelers or migrants between established systems easier, they have colonization value too. First, populating a new system enough that they want to colonize an empty neighbor is a slow process, while settled systems a few expansion spheres backward might have a ready population supply who can travel out to the frontier more quickly with such a system in place. Second, while handy for slowing down if you've an array at the other side, it can be used simply for speeding ships up, sending out ships from established systems at higher speeds who can then use their onboard fuel to slow down, doubling their default cruising speed. Third, an automated von Neumann probe or seed ship might be able to build a small beaming array at a destination system able to slow down a colony Ark ship that was inbound behind it, or even to slow down another automated probe that can build a bigger array. As a conceptual example, imagine a large fleet of Ark ships moving toward a system and carrying some fuel, but not enough to slow themselves down. They transfer some of that fuel to a probe and launch it forward, and as it approaches the incoming star, it extends mag sails and solar sails to slow on solar wind and sunlight. This probe uses the energy to fire a beam backwards at a second probe, which is similarly slowing down. As the first one plunges into that star, having not been slowed enough, the second performs the same operation, but plunges into that star even slower. Maybe you only need one or two probes, maybe you chain dozens together like this. Indeed, you could potentially chain them together literally by a tether if you wished, which might have some benefits, but eventually you get some beaming systems that don't plunge into that star and instead orbit it, beaming energy back to slow your fleet. Similar methods can be used to let vanguards and picket ships operate near larger fleets, along with trailing vessels that are stopping to collect material from interstellar objects found between systems, establishing relay points, or coming from behind the fleet in the form of ships sent later on carrying additional colonists or gear or raw materials or reinforcements. We'll discuss such approaches and methods more in our upcoming episode on battle fleets, but our focus today is on colony fleets and their ship types, and speaking of that,
Ship types.
we have a number of ship types we want to discuss today, and each has its own special flavor of how it approaches colonization and alters the settlement strategies available. For instance, if you have fast and light vessels, our first category, you obviously do not pursue the colonization strategy. That's more the approach of our second and third categories, micro-jump ships and generation ships. We'll be devoting a few minutes to each of these categories and discussing them more of a conceptual order than alphabetical. In many cases, you can see the ideas evolving from early science and sci-fi speculation to more current ideas. I should also note that in many cases these might be multiple ships, a fleet sent out to settle a new system, and the fleet may have mixtures of ships, potentially arriving in waves. The categories of ship are fast and light ships, which circumvent the super long interstellar travel times problem, micro-jump ships, which assumes you're using relatively low tech and simple vessels to colonize very short distances, generation ships, which assume the voyage is so long that it's your descendants of the original travelers that arrive. Then we have sleeper ships, which seeks to preserve those travelers by some form of stasis, freezing, or hibernation. The alternate approach are Methuselah ships, which seek to preserve those travelers by extending their lifespans through life extension technology. Gardener ships attempt to contemplate what happens when we fuse Methuselah ships and generation ships together along with superior automation. von Neumann probes take that automation a step further and assume at least some limited AI is involved and being used to operate self-replicating spacecraft. This extends to seed ships, which are automated vessels that do a lot of your colonizing for you in advance, while data ships assume sophisticated AI and uploaded human minds do your space settlement for you. Collector ships posits a different strategy, using those automated self-replicators to journey out and return with resources, while planet ships move beyond the interstellar strategy to contemplate voyages across the galaxy or to other galaxies. Finally, we have a number of hybrid varieties to consider.
Faster-than-light ships.
Faster-than-light, or FTL ships, are our classic science fiction approach to getting around the galaxy, and we discussed the various approaches to FTL and the difficulty of making it work in our Faster-than-Light series, covering everything from quantum entanglement to time travel, warp drives, wormholes, folding space, hyperspace, and various other suggested means of cheating reality. As channel regulars know, I do not believe we will ever find a way of moving around this universe faster than light. I do not know any other physicists who think it particularly likely either, including the ones famous for warp drives or wormhole concepts. But my own pessimism is not simply from physics, but the Fermi paradox and our discussion today. FTL not only makes interstellar travel vastly easier, it makes intergalactic and even inter-supercluster colonization possible by a hybrid of the same ship types we'll get to momentarily, such as FTL generation ships or FTL sleeper ships. All at the same time, you see settlement efforts jumping to the nearest inviting target and probably only backfill less attractive systems or planets as the leading edge of colonization to inviting new empty prospects moves far beyond them to make them attractive again by proximity.
Micro-jump ships.
Micro-jump ships represents the first approach to getting into interstellar colonization without FTL drives, and essentially are mundane spaceships whose approach to handling the long distances and travel times of interstellar travel is simply not to have them. We don't need them for getting to Mars or Venus or Titan, for instance. The key notion here is that since any ship designed to get to other star systems needs to be incredibly good at recycling material and keeping itself running for long times, it probably implies you have the technology to make very long-term habitats in the interstellar void. And while that void is sparser than any desert, it still has plenty of asteroids and icy bodies, and even dwarf and rogue planets. We estimate there are hundreds of billions, if not trillions of icy bodies in our solar system's Oort cloud, which we believe stretches over a light year out. Our usual notion to settle 500 billion stars in this galaxy is to leapfrog out from them, colonizing a system, or new expansion sphere of systems, and then letting them colonize the next sphere. You could likely settle space by tiny jumps to each of these new interstellar icy bodies and minor planets, as opposed to jumping between star systems to new star systems. It is very likely we could find several dozen decently sized rocks that represent a modestly straight line to Alpha Centauri or any other star. They'd probably zigzag a bit, and nothing in deep space is really stationary on the scale of thousands of years. But even 40 or so rocks 10 miles across or more would likely have abundant resources for a deep space settlement and let you have an effective relay path of increments of about a tenth of a light year each. That makes for communication times on an order of a month, which was common enough historically, and means even a ship using a fairly conventional ion drive and nuclear reactor should have no problem carrying people and cargo to the next target location in reasonable human timeframes. In all probability, you could find several thousand settlement spots along your corridor, though some may be longer gaps than others. And were this the case, even with modern and tested spaceflight technology, we could reach a new star system eventually, and without any individual crew member or ship journey lasting more than a year or so. You simply need a power supply, but odds are you have a plentiful supply of uranium and thorium out there, even if we never got fusion working. And we have power beaming options too. Essentially though, any ship able to reach the nearest star in a single lifetime needs such an abundant energy supply for its drive system that it dwarfs the life support needs of that ship, or of a large number of small outposts, which we might think of as a chain of islands or archipelagos between the rich continents of inner star systems.
Generation ships.
Generation ships are the alternate approach to handling the long travel times for passengers to new star systems, as it recognizes that it generally takes way less energy to supply air, water, and food to a traveler for a trip taking twice as long as it does to double that ship's speed so it can get there in half the time. We already have ship designs that could plausibly get to the nearest star systems in less than a lifetime, but would leave the crew quite old to do the work of settling a new system. Not a great way to spend your retirement, scratching out a life on a barren planet. And of course, we generally assume their descendants are doing most of that settling anyway, while growing and multiplying rather than trucking in billions of people from Earth. Generation ships or arc ships are a popular topic in both science and science fiction, and was the strategy we contemplated in detail in the first 3 episodes of our Generation Ships and Interstellar Colonization series, Generation Ships, Exodus Fleet, and Exporting Earth. One critical notion to them is that they must be very large. You're not only trying to support a large human population, but also several thousand other species of animals and untold numbers of plants and microbes. This is the reason these are often called interstellar arcs, and we tend to assume we need a lot more than 2 of each kind and a ship 300 cubits long, given the scale of the journey and the absence of divine assistance, though we have some technological assistance that can help with these problems that we'll get to. Generally, we imagine using an entire O'Neill cylinder for this purpose, massing several gigatons, and which would require several gigawatts of power generation as a result. This is not a problem in and of itself, since that could be accomplished by conventional fission reactors, and even multiple centuries worth of energy supply would represent minimal cargo. Indeed, since you could use breeder reactors, you could be using regular uranium as your outer hull, as it makes for good armor. Your typical kilogram of uranium contains around 24 million kilowatt hours of available energy, and you might go through several kilograms a day, or several dozen tons a year. But even a century-long timeline, we're contemplating a few dozen kilotons for supplying energy for life support to a ship many thousands of times more massive. Alternatively, the default drive system for these is an Orion Drive, propelled by launching kiloton nuclear devices behind the ship to explode and shove it forward. The kinetic energy of a gigaton of vessel moving at 10% of light speed is about 500 trillion joules. And realistically, you'll need to spend at least an order of magnitude more energy than that to get the ship to that speed. On the flip side, basic life support for a human crew, including fairly lavish hydroponics and garden spaces, would run more on an order of 1 trillion joules a year, meaning even 1 million colonists living on that ship for 1,000 years runs well under 1% of the energy budgeted for just moving that ship to the destination. Energy not being free, this becomes the basic conundrum of the generation ship. How small can you make it work, and how slow can you send it? You have a lot of factors piling in here that we've discussed at length in other episodes, but some key points are worth noting. First, this concept dates to an era with less knowledge of biology than we have now, and that new knowledge has both solved problems and raised others. We can get away with a much smaller population without fear of mutants if you've got a lot of frozen sperm, eggs, or fertilized embryos stored around. This has some time constraints to it. We know frozen sperm can still work at least 50 years after freezing and may be good for longer stretches, but as we'll discuss in the sleeper ship section, there are some limits here. DNA can also be stored digitally for indefinite periods, and also transmission at light speed, which will come up in our data ship section, but can also be printed, albeit with great difficulty currently, from that data into a DNA molecule for insertion in an embryo. This means a generation ship should be able to avoid having its crew become more inbred than a pharaoh, and the same for its critters, allowing fewer of them. They also likely have much better technological means of addressing the various health issues inbreeding tends to cause, which also tend to get a bit exaggerated in popular discussion. So we can contemplate smaller ships, and ones where the food is mostly made by hydroponics rather than conventional farming, including for the critters. The other problem there, though, as we detailed in Exporting Earth, is that a lot of critters do need parents to raise them, or they turn out weird if they don't simply die instead. So you can't go too small with your ark size, though we can contemplate some weirder options like android or virtual animals raising infant critters, and we'll do so in a bit. Second, while going slower has its advantages, in that it takes way less energy and also cuts down on the hazard of space dust and micrometeor damage, time also makes you break and leak. No matter how you cut it, a spaceship and crew are always in a race to avoid running out of reserves of raw materials and spare parts. Indeed, if you can't manufacture spare parts in motion, your ship can't afford to travel longer than the shelf life of any vital components for repairing that ship, sustaining that crew, or achieving a sustainable settlement at the end of the trip. Technology has helped a lot with this problem as it contemplates more automation and options like 3D printing, but you're still leaking air the whole way, and water, and everything else. Losses simply accumulate, and you can't stop for resupply without actually stopping, meaning you need to completely refuel too, and take on all the extra wear and tear any ship experiences with its engines on, as opposed to simply cruising through empty space. Third, the crew can have a rough time trying to stay on mission and mission capable for centuries or even millennia at a time, starting with the problem that none of the people that were either born on the trip or began it as children were able to give informed consent to participate. They also probably cannot be expected to be the cream of the crop, whereas by default we can recruit highly motivated and talented people for Generation 1 on such a ship. Their kids still have to be raised and educated to fill each of those slots from a much smaller recruitment pool. On the one hand, they have both nature and nurture on their side, smart biological parents who are also raising them and in the work environment they'd serve in. But that is not a magic wand for ensuring you end up with a replacement crew that matches the prior generation's abilities and enthusiasm, and we might have several generations involved, or even many dozens. In the book Neumann by Marina J. Lostetter, they try to solve this by having each new crew member be a clone of an existing crew member who is raised into their purpose on the journey, although it's still not smooth sailing for them either. Going faster or having a larger ship with more people can help with that, but becomes part of that balancing act of more expensive ships being harder to send, or a desire to send many smaller ships to many stars. In the early days of contemplating this travel, it was assumed you had to worry about losing knowledge, as these ideas date back to physical and heavy books and vinyl records. We can dismiss that problem in the modern compact digital age, though you do have to worry about intentional sabotage or scenarios like your captain maintaining power over the crew and passengers by keeping all the copies of critical data in booby-trapped archives, saying that if anything happens, the data will be destroyed. Someone calls the captain's bluff and finds out it wasn't one. This is the real issue on long enough timelines, and we explored it in more depth in the episode The Million-Year Ark. Population control can be an issue on these ships too, though that can be addressed in many ways, and it can include population drop. This, along with the worry that you might not get enough volunteers for colonization in the first place, which I doubt, is an example where if nothing else works, you can always start busting out the cloning tanks or uploading minds of recruits and downloading multiple copies of them to various android or clone bodies. But again, I don't think that's a concern you'd face often. Also, in spite of what Star Trek claims in its episode Up the Long Ladder, there is no such thing as cloning fatigue, certainly not on century timelines, and stored DNA can handle that and genetic bottlenecking issues on your cramped ship. Overall, Generation ships remain the lead candidate for interstellar settlement, and our only viable one besides the micro-jump approach under current technology or those technologies that are comfortably in the solid theory or prototype phase.
Sleeper ships.
Sleeper ships are an example of another approach to space colonization that simply seeks to circumvent travel time by not having the crew and cargo experience it. This might involve freezing or hibernation or some advanced stasis technology that effectively stops time. We can freeze people now, but can't thaw them, not alive anyway, and as we discussed recently in our episode Planetary Archives and Stasis Vaults, we have only a few very limited and dubious pathways towards practical technologies for stopping or massively slowing how people experience the passage of time. Even if we do freeze people, as we explored in our episode on this concept, we are limited to a few thousand years before the radioisotopes in their own body will give them lethal radiation poisoning, though there are get-arounds for that, like purging those isotopes from someone's diet for a long while before the mission, or simply better medical technology, which is sort of implied by the ability to thaw them anyway. After all, you aren't even vaguely asleep when frozen, you are utterly dead and your cells terminally damaged. It is possible a civilization that was confident of developing new technology or very desperate might send a ship with lots of frozen people on it before they could revive them, hoping to send the tech along later when it was discovered. If it was also doubling as a generation ship with a smaller living crew, this might be more viable. If it works though, sleeper ships are a great way to avoid loss of the original crew and supplies. This isn't likely to be a universal state on that ship though. Not everything is going to be frozen, some things wouldn't need it, some wouldn't survive it, and you may have crew awake for the journey and colonists frozen instead. Freezing people itself is easy and very low energy to sustain, even compared to the low cost of life support in a ship's energy budget. Nonetheless, that life support budget is still small compared to the ship's flight energy budget, so maintaining a giant freezer tomb section and a spinning habitation drum for a minority of the people on board who are awake is very viable. You might trust AI for running the ship. Indeed, it's probably more capable of running a ship that's been flying in a straight line for a century than a human anyway, even if it is a fairly stupid AI, and less likely to go stir-crazy from the flight, or axe crazy. I would still wager on a smaller crew awake, maybe 1% of the total human passengers, and the same for the animals. A few pets on board awake, while most of the critters make the trip on ice. Indeed, for most mammals, you could get away with just one frozen female and a lot of frozen fertilized embryos for implantation, and if you wanted two, it's for redundancy rather than a male. That's not generally the intent with crews of interstellar arcs, though it is occasionally noted that you can keep a larger female crew since they eat and breathe less than men on average. As we've noted repeatedly though, life support needs for the crew outside of the micro-jump approach are so trivial compared to your flight energy as not to be a major consideration in crew makeup or lifestyle. It's handy that virtual reality and digital libraries can let us keep our knowledge and recreation compact and low energy on these ships, but it's also not terribly necessary either. Space is not at a premium in space, because there's just so much of it. So your ships can get away with having tennis courts or swimming pools on them. You just multi-purpose a lot. Your water reserves are your swimming pools and fish tanks. You are also still leaking all these things, and thus cannot simply opt to go ultra slow and save tons of energy this way. You also cannot assume that there's no competition at the final destination for who arrives first. Take 1,000 years to get to a neighboring star, and you may find a dozen different missions have already arrived centuries ahead of you, claiming all the good worlds and offering you little to pick from, or even a violent greeting. By default, I would expect on a ship with tens of thousands of colonists, frozen for a voyage of a few centuries, you might have 1,000 crew who each agreed to do a 6-year shift, and maybe got some dibs on prize colonization spots or gear as a reward. Getting paid by the space agency back home is a rather dubious concept, though great if you can trust your account to keep existing and gaining compound interest. 6-year shifts for 300 years lets you have 50 shifts of 20 crew each, though you presumably are waking people up singly or in small groups to stagger replacement and adjustment. One person roughly every 4 months, and helps you check your freeze-or-thaw method is working and perform complex maintenance, get information and updates from home and act on them, and have folks awake to strategize as new data comes in, both from the target system you're approaching and getting better data on, and from home and other colonies, who are all constantly coming up with new and better approaches for settling strange new worlds under alien skies. It is also worth remembering that arriving a new planet does not mean everyone now needs to be woken up. It may be best to keep most of the folks frozen for years or even decades as things get set up, and so as not to overload your fledgling colony. So too is a great way to send second and third waves of colonists. A big tomb ship only needs a cubic meter or so per frozen person, and as a second wave vessel could benefit from beam assist methods of both speeding and slowing the ship down, allowing faster and lower energy transfer to established colonies. A ship the size of a Nimitz-class aircraft carrier, which is rather tiny for a generation ship, could carry 1 million frozen people, whereas the gigaton mass ships we typically imagine for a generation ship could move an entire planetary population on ice.
Methuselah Ships.
One of the problems with sleeper ships, though, is how to wake people up, especially since if they're frozen, we really mean dead and in need of resurrection, or at least resuscitation. Generally, we assume advanced medical technology can repair their cellular damage, but this same technology could almost certainly be used to restore someone's cells while they were still alive and much easier, allowing very protracted lifespans. It could also very likely be used on other critters, and indeed life extension technology is likely to first be achieved on lab rats, not people, and probably be commercially available for our pets before us, since the approval process would be smaller. A Methuselah ship contemplates handling the very long time increments of space travel the same way a generation ship does, but without the issue of loss of skill. Quite to the contrary, folks on a ship for a century not aging, who were already experts on something, have had a whole century to keep getting better at it, or cross-training. Indeed, you could send untrained folks along, and they could probably train on the voyage. As spouses or children of primary volunteers presumably often would too, which might be appropriate for all the skills you don't actually need during the journey and only need on arrival, especially in earlier missions where we often won't know all we want to know to colonize a system best, and we'll have updates from home and neighboring expeditions tossing in suggestions regularly. These have 3 basic problems though, beyond us not having this technology yet. Though for that at least, I would be surprised if we had launched a single interstellar colonization mission before we had acquired this technology, as I don't expect the former to happen this century, but I do think there are already people alive now who will survive to see radical life extension become household technology. Our first problem people tend to bring up is boredom. I tend to think this gets exaggerated because most of the time when folks talk to me about being bored, it's the experience of waiting around for something with nothing to do and inherently temporary. You are stuck in the doctor's office till they see you, and doom-scrolling your phone is your only option. Pre-smartphones, you went through the magazines there or brought a crossword puzzle. It didn't imply boredom with life, and while I could contemplate boredom after living millions of years, hundreds or even low thousands seems implausible. I often enjoy reading or listening or watching a book or film more than once, and I am years behind on my reading and watching lists. If you launched into space with just modern available options, I'm not sure how you could get bored to death with the entire library here on YouTube, or all the other podcast and streaming options that many of you use to tune into this show by instead. You still can get bored, we all get saturated and turn it off, but then you go play a game or have some dinner with friends or do some work or go for a walk, and now you're not bored with the TV or library anymore. We are wired up to get saturated that way. We could probably alter ourselves not to get bored at all, but it really shouldn't be necessary. There's no turning around, so you're stuck on the mission till it arrives. Thus, we are not talking about getting bored occasionally or a lot, but bored to actual death, and that seems less likely. That does raise our second problem though, which is a loss of interest in the mission. This is more a concern for generation ships where your descendants might not care about the mission as much, though they may be passionately devoted to it too. Nonetheless, people's interests do wane, and while it wouldn't likely endanger the mission at an existential level, you may gain the benefit of a ship's engineer with a century of experience, but also one who is just phoning it in these days and wants to spend the rest of the trip on ice or retrain to be a shuttle pilot. You shuffle and cross-train, and generally folks are going to keep much of the knowledge from their prior career, especially if you ask them to spend 1 workday a month still doing it. That's for maintaining the mission. For quality of life issues, you just make sure folks have lots of options for other interests to arise and be pursued. Of course, for a lot of folks that means having friends and a crew big enough to support wide and changing social circles, along with getting married, having kids, raising families, raising grandkids, which can be problematic on a ship sailing the ocean of the night with no resupply in sight. Having kids, both human and animals on board, is our third big problem with this type of ship, though not entirely unique to it, since generation ships need to worry about replacement population and growing too numerous too. But it invariably means growing your population on a Methuselah ship, and unless you've got folks agreeing to go on ice for the remainder of the voyage, which is probably viable in a lot of cases, you've got a growing population problem, pardon the pun.
Gardener ships.
Gardener ships are our first and biggest example of hybrid ships, as it merges several of the approaches together. See our episode Gardening the Galaxy for an in-depth look, but the key concept is that a higher-tech civilization, like the ones probably able to send interstellar ships out to settle new systems, probably do have extended lifespans, freezing-thawing technology, and very good automation. They likely can then incorporate the generation ship, Methuselah ship, and sleeper ships concept in to create a better hybrid method, along with some other options we've still got to discuss. Getting to a new system is only part of the colonization process, and honestly, the smallest part of it, if perhaps the hardest. Often in fiction, we see them arrive and they either land the ship or shuttle down from it to a planet and leave the empty behemoth in orbit. This really is not the best approach to colonization, and indeed your better approach is to treat that ship like one immense factory churning out everything you need to supercharge your colonization effort, including your space infrastructure, which you should be building before landing on the planet. But a true generation ship needs to be able to produce every single thing that ship needs to do its mission, including complete replacement of every part and every crew member. And that means when the mission is done, you've arrived and unloaded your colonist, you have a giant ship in orbit that is able to absorb raw materials, which are now plentifully at hand, and recreate anything you need with time, including another ship if it came down to it. Well, there's one thing you have plenty of on interstellar journeys, and that's time. And when you have a ship full of passengers on a journey, they haven't got much else to do but produce gear for the end of that journey, improve their ship during that journey, and have families. If you've got an effectively ageless population, one that grows even at just 2% a year, which is hardly a baby boom given that folks aren't dying from old age, then a crew of 100,000 that sets out to colonize a planet a century away is going to arrive there with 724,000 people. 724% more than the original mission called for, and again, life support on the trip isn't really a big issue, so it wouldn't be hard to plan around that sort of growth, and you have a large workforce to transmute raw materials into more living space and life support equipment in that time. So your future planetary governor, whose job we'll be exploring more next month, might say, "Great, with 7 times as many people, we can settle this place 7 times as fast." While the captain of the ship might say, "Great, with all these extra people, I can resupply my ship and head off to another system." And the ship's executive officer can say, "Great, with all these extra people, we have the resources and manpower for an extra ship." Because that XO knows they're not getting promoted to captain until there's a new ship or the captain dies or retires, which is a problem in a long-lived society. Indeed, one that some of the colonists born on that ship might feel too, and want to settle a different continent or even planet in that system, or to found a few dozen asteroid mines. And some of those folks might want to go home to Earth, and with 7 times the people originally planned to achieve settlement, they can get a lot of other projects done. Indeed, being further helped by a century of new technology, techniques, and updates from back home, they probably could do it with a lot less people than originally planned. So they could build a ship to send home, restaff the ship to go to another new system further from Earth, build another ship to send to another destination, and start several more modest settlements in that star system, while still settling the original planned location more robustly than originally planned. All at the same time, it handles the problem of limited upward mobility a ship of long-lived passengers and crew has, because people born on the flight can go up when the divisions occur, leaving as second in command of some department to head a new department up on one of the new settlements or ships, and be replaced in kind. So too, tensions from rival factions growing during the trip can be alleviated by knowing they shuffle around to the next stop, and if it gets too bad, they can go on ice to make the wait easier, opening a spot for someone else in the meantime. And this is the core concept of the Gardner ship or fleet, as it imagines small fleets of ships leaving out from Earth that pause at new systems to drop off colonists, take on more raw materials, and then spend the flight to the next system breeding up more people, building a few new ships to add to the fleet during the flight, and also building and expanding their own ship when not working on preparing skills and equipment for the destination. Fleets can subdivide on arrival, with some breaking off to one or more new systems while others stick around to serve as trade freighters in system or to neighboring newly settled systems, and others head back to the system they most recently left to establish trade with their last colony in the chain and take back passengers who may have decided they don't want to be part of the colony effort anymore, or even journey all the way back to Earth, awake or on ice. All in all, the Gardner fleet approach seems the best one for long-term but rapid galactic expansion by something akin to a modern human civilization.
Von Neumann Probes.
One issue a lot of colony missions will face is not having detailed enough information before they leave for the destination. And even though as they approach they can see better, astronomy isn't best conducted at highly relativistic speeds for a number of reasons. This is where advanced probes that can do flybys, or even stop and examine a system, come in handy. The von Neumann probe is the logical extension of this, as it assumes the basic intelligence of any probe able to maintain itself for a journey and operate independently is probably sufficient to let itself replicate too. Thus the von Neumann probe, or Astro Chicken as it's sometimes called, arrives at its destination system, lands on some rock, extends some solar panels, and begins using that energy to eat up that rock and process it into more sophisticated detection equipment and laying eggs of other probes that will set off for other systems or other spots in that system. Then it will build a relay to be able to transmit its data and its children's data back to Earth, or to the previous relay, or to the fleet arriving with colonists. Outside of science fiction, this does not in any way imply advanced AI. Remember that plenty of organisms on Earth self-replicate without a brain of any kind, and navigating interstellar space is not very difficult. We'll discuss self-repairing machines in depth later this month, but there's a lot of very good safeguards you can put in place to avoid the usual sci-fi concerns of these self-replicating probes turning homicidal or going all paperclip maximizer. There are legitimate concerns about this basic concept. It's just that decades of folks discussing it have basically addressed them all, and they're insanely useful, so you would expect us to use them a lot after field testing those safeguards. More sophisticated versions raise more risks, but offer lots of additional benefits, such as being able to have an automated vanguard force arrive and prepare a lot of your space infrastructure for you, like beaming arrays that could slow larger vessels down to permit them to brake without onboard fuel and journey faster as a result. I usually assume a von Neumann probe is not anywhere near being a sophisticated or general artificial intelligence. It doesn't require it, and we have other categories that include that, such as seed ships, and my philosophy with AI is to never make it smarter than the task needs. See Dennis E. Taylor's wonderful Bobiverse series, starting with We Are Legion, for an example of a smart von Neumann probe, specifically one with a human mind uploaded into it, Bob.
Seed ships.
Seed ships are meant to be automated vessels, or mostly automated, that can arrive at some system and get the colony started. Depending on their sophistication, they might be relatively dumb AI just sent to build some basic apparatus like power collectors, automated asteroid mines, and space elevators, or they may be an advanced AI able to grow life from frozen or digital DNA, and even raise life first in growth tanks and later as an actual parent figure for fledgling human colonists, possibly as TV, holograms, or android parental interfaces, maybe even a cloned biological body. Seed ships are usually envisioned as a low-resource approach to space settlement as they need not travel fast, but can be much lower mass than a classic arc ship or sleeper ship, and thus are cheaper to build and cheaper to push to high speeds too. These are often seen as the ideal way to colonize space, though also disliked for being entirely automated. For a lot of us, the point of settling space is to do it with humans, and partially because we are humanists, but also because people in advanced civilizations can have issues finding a purpose to existence, and settling the galaxy is a pretty good one for that. So completely automating it is potentially non-ideal. Often though, the seed's ship's AI, which might be a post-human mind anyway, might simply be someone's uploaded mind that again might transfer to an android body, might simply be setting up the basic infrastructure so frozen colonists following behind can arrive faster and settle faster. And against the notion that we are taking all the challenge away, I should note that arriving in an alpha base that's basically some pre-made domes in the middle of a planet less hospitable than Antarctica is still pretty challenging. As to the point that they are more economical and quicker, that's mostly hand waves. Ship speed is mostly about the engine design, not the total available energy or money a civilization has. If your basic fuel is deuterium, then there's enough of that lying around in our gas giants to send 1 billion giant colony ships out into space and barely dent the local supply. The top speed of a robot ship version of a human crewed ship is the same, though they can handle faster acceleration, meaning on shorter voyages they do get there much quicker. They would beat you to the moon and back. But on longer voyages they shave off a little time only, albeit that makes them great in a vanguard role. There's also no guarantee that you have a drive that can produce high acceleration rates, or deceleration. Generally, the rule of thumb with space drives is the faster you want to go with the same basic technology, the slower you want to accelerate. All interstellar ships need lots of frontal shielding too, a point we'll come back to with data ships in a moment. Seed ships do not necessarily have to be self-replicating, but the same logic applies as with an interstellar vessel. They spend so long traveling that they probably need the ability to replace every component, thus probably have an intrinsic ability to self-replicate. You can sabotage that by having some specific component it can't do without that is relatively durable and long-lived, and which it doesn't have the ability, files, resources, or permissions to recreate. Strictly speaking, you can do this to regular colony missions too, to prevent them going their own way or further colonizing without permission, something we contemplated more in our Fermi Paradox episodes, the Chronos Scenarios, and Interdiction Hypothesis.
Data ships.
Data ships are something of a subcategory of seed ships, but a big enough one, and with a few key differences, that it merits its own heading, even if our episode Seeding the Stars covered both seed and data ships together in it. They essentially seek to remove any biology from the equation, at least for transport. This could be by having entirely digital minds on board, AI or humans who have been uploaded, or post-humans, the delineation there is a little ambiguous. Once they arrive, they may start terraforming a planet and growing people, either babies they can raise or android or cloned bodies to download their minds into. Or they may be digital humans planning to turn that star system into vast collections of power collectors and huge databanks to serve as the substrate for their digital civilization and the virtual worlds they dwell in there. Or they may be other types of AI. We would not usually expect this to include a seed for a singular intelligence though, since generally a megamind of the Skynet variety in a no FTL universe cannot really benefit from creating another copy of itself light years away. That propagates a species, but if that's not your objective, all you propagated was a rival. They have other better approaches we'll get to in a bit. As we noted earlier, you can print DNA from digital files, and while there's a lot more to growing an organism than having its DNA, this does lift a lot of the concerns about time and radiation that sleeper ships and seed ships have. Now, digital information is radiation sensitive too, the more so the smaller and more compact that data is stored. So while folks will occasionally suggest pencil or even needle-sized ships, this really is not viable at high speeds, which is basically the point of a ship that small. It is also inherent to such technology that it can build itself or build itself bigger, so going small is really rather unnecessary. A single medium-sized asteroid, of the kind we have thousands of in this solar system alone, might contain enough material to build 100 trillion ships, and we don't even have 1 trillion systems in this galaxy to send them to. So beyond that they could stop every few hundred light years to build more locally without much slowing of expansion, and ignoring that such an asteroid would not represent even 1 trillionth of the matter in this solar system, you could still send 100 trillion big probes out from that one asteroid, making needle-sized ships utterly pointless anyway.
Ship shape and collisions.
As a side note, as we finish our discussion of the core ship concepts, we always assume interstellar ships are much longer than wide, thus pencil or needle analogies. We would also like a sharp front rather than a flat one to allow colliding material to deflect away and partially cut down on the impact damage. Almost all the risk to them is in that forward cross-section, so we try to keep them long, potentially like train cars even, or sausage links that might be able to break into mini sub-pieces, ships or habitats at the final destination or refueling sites. As we discussed with the Gardner ship design, with raw materials, you can potentially be building more ships along the way and breeding up and training new crew. Digital crews don't really have this time limitation, as they can presumably rapidly copy themselves, though again, at the interstellar scales of time, this is not as huge an advantage as it initially sounds. Interstellar collision avoidance is a topic we covered in detail in our episode Interstellar Travel Challenges, but when you are moving at 1% of light speed, a 1 kilogram rock is hitting your ship with the power of a 20 kiloton nuclear bomb, similar to what was used on Hiroshima at the end of World War II. And spotting something like that 1,000,000 miles out, 4 times the distance to the moon, would be rather difficult, but even if successful, leaves you only about 10 minutes to react. At 10% of light speed, that rock is 100 times more powerful, 2 megatons of nuke, and you have 1 minute to spot and manage it. At truly relativistic speeds, you have to be able to spot something the size of a pea that far away and need an automated laser able to roast it in milliseconds. On travel between any 2 neighboring stars, you're much less likely than not to encounter such a hazard. Space really is quite empty, but the faster you go, the smaller the object that can hurt you, and the smaller objects are much more common. Plus, you need to spot them further out so you still have time to react since you're going faster. So go faster, and you need to spot smaller bodies and further away. Your odds of anything rise with your ship's forward cross-section, so a ship 10 times wider thus has 100 times more front area and is 100 times more likely to find that murderous pea in the interstellar void. Thus you probably don't make habitation drums tens of miles wide when something 1/4 of a mile wide is probably comfortable and can just be made longer.
Collector ships.
One problem all these ships have is that they can't stop midway through for refueling or replenishing raw materials. So too, one problem with colonization is you are potentially creating rivals, not partners or additional kingdoms under your control. The collector ship gets around this, and is basically a von Neumann probe or seed ship that is tasked with mining a system out and returning its components to the core system or systems. As we discussed in our episode on interdiction hypothesis, one approach an interstellar empire might have is deciding it couldn't maintain cohesion beyond, say, 25 light years. So it builds those systems up, then strip mines a sphere 100 or more light years around it with automated collector ships so as to leave it a barren desert no rival could grow strong in or easily invade through. Whether confined to a single system or a handful, you can pack most of a galaxy into such a volume. So you aren't going to be at much risk of overfilling your core territory by reaching out too far. Those collector ships do not need to be smart, even for mining gas giants or starlifting the local sun for metals. As is often the case with simple automation, you don't make general minds who can do everything. You make a lot of specialized organisms who each excel at some small part of the process. You're not in a rush either, so if you have to dispatch some replacement collectors with some improvements every few millennia when some cascade failure occurs because you kept things a little too simple, it's not a big deal. Whereas hurrying or giving them too much brains might be a very bad idea. A subset of these collector ships, which we might call resupply splinters, is valuable to colonization fleets planning to use your vanguard to be in collection in front of you, or sending off a small piece of your fleet to slow down at some resource spot in the interstellar void and set up mining operations on it. They can later catch up with the fleet, as can goods they harvest, by launching them slightly faster than the fleet is moving and with a little slowdown fuel, or even none at all, where a ship can rendezvous and catch the cargo pod magnetically or with a tether and reel it in, gaining some speed in the process itself. It would be very situation and technology dependent if this was a better option than simply stopping the whole fleet at an occasional destination to take on supplies and do upgrades. But it gives fleets an option besides stopping at their original location or a system with very little additional delta V needed to reach it. Low-mass automated collector ships are a good approach for this, since they won't need much of the fleet's fuel to slow, can brake very rapidly, accelerate themselves and cargo pods very rapidly, and you don't have to risk any crew being lost or stranded on some rock in the middle of the interstellar void. This approach may be vital to ships moving at very high speeds to other regions of the galaxy, or other galaxies not wanting to lose any speed or time, but large enough to send sizable splinters off from itself.
Planet ships.
Planet ships are all category of extremely large and sustainable vessels used for voyages which do not plan to stop for many tens of thousands of years, or even tens of millions. While in theory this could be an actual planet like Earth being moved to a new solar system, such as to migrate to a new star when our sun begins to die, we generally are talking about scale rather than nature. Such a ship may look like a planet and contain as much life, but would likely be built from the ground floor up. It is intended to have so much redundancy of resources as to be akin to a planet, such that it could continue operating even if entire civil wars and civilization collapses occurred on it during the voyage. Indeed, it might survive the total extinction of its creators and the delay, while one of their smarter species of pet evolved intelligence and civilization, which a journey between galaxies might give time for. It would have enough resources to be able to send out smaller and faster vessels, indeed entire armadas, to potentially harvest or colonize systems along its way and to act as its vanguard and outriders. Such immense ships might be dispatched toward black holes far across the galaxy, where they could be sent at very high speeds and use that black hole as free braking sources. Or they might be dispatched to different galaxies or even across an entire supercluster, and able to maintain civilization there indefinitely. A larger variation of this is where a star or black hole is used instead of a planet, and provides its power supply. See our episodes Planet Ships and Fleet of Stars for discussion of their engineering, uses, abilities, and function.
Hybrid ships.
Our last category of ships are hybrids of those we've already discussed. Much of the Gardner ship is a mix of Generation and Methuselah ship, and many are simply food for thought. Examples of this could be a seed ship that was a sleeper ship too, allowing mostly automated construction of the settlement, possibly including growing plants or even animals, before thawing its people. We could also imagine a hybrid process, where a seed or data ship arrived and was followed by a dedicated sleeper ship containing millions or even billions of settlers. A colonial fleet might mix and match any number of these options, and even change over time. For instance, a Gardner fleet might be constantly dispatching smaller collector fleets and micro-jump ships to settle a wide corridor of space around it as it passes from one star to the next, mining or colonizing thousands of minor planets in the void between those two systems. This might be done with the intent of leaving behind a powerful pushing array to allow high-speed, low-energy transit between the parent system and the colony world, which might see wave after wave of other ships following behind to people the corridor and new system. It might also be done with the intent of allowing a very high bandwidth data relay between those systems, one strong enough to allow transmission of entire uploaded minds, so that digital colonists or visitors could arrive at light speed, or that people might have their minds scanned and loaded on arrival into an android or cloned body. Needless to say, most of these methods also hybrid well with FTL, if you ever get it, and it would be my general expectation that we will use a mix and match of these methods, using those which we deem best or most preferred and combining them with others when it suits us. A lot would depend on your colonization goals and strategies too.
Colonization strategies.
Your technology and goals will control the strategies you pursue to pick out systems for colonization. In science fiction, we often see only systems with ideal yellow suns like ours and a planet of roughly Earth mass in the habitable zone being colonized. We will call these prime systems, and we loosely assume somewhere between 100 million to 10 billion such systems in our galaxy. We don't have enough exoplanet data on Earth-sized planets yet to narrow that down further, and it also depends a lot on how Earth-like that planet needs to be in mass or composition, or if it needs to be in a classic habitable zone, since we can't employ terraforming methods like solar mirrors or shades as we might on Mars or Venus. We'll talk more about some of those early terraforming options near the end of the episode, and terraforming probably needs its own compendium episode down the road. Though the sheer length of compendium episodes tends to limit me to one a year, it's always a good idea not to bite off more than you can chew, which applies to terraforming too, and controls our choice of systems to colonize. After all, making a home on any new world would make settling the Arctic or Sahara seem inviting, and you only need to carry your settlers and gear hundreds of miles, not hundreds of years, to get to those.
Lowest hanging fruit.
By default, the places we imagine colonizing are the 100 million to 10 billion prime star systems in our galaxy that will contain the best Earth analogs, with a yellow sun and a planet where we can have surface seas and an atmosphere. These, particularly the ones closest to Earth, become our low-hanging fruit, and presumably represent somewhere between 2% and 0.02% of the star systems in this galaxy. Indeed, of the over 130 stars and known substellar objects in our immediate neighborhood of 20 light-years around Earth, only 7 of those are G-type yellow stars. Our own sun, called Sol, Alpha Centauri A, Delta Pavonis, Tau Ceti, Eta Cassiopeia, Sigma Draconis, and 82G Eridani. You've probably heard all of those names before, and precisely because they are the popular early destinations for colonies in science fiction. We generally assume, especially early on, that we want to go to these systems first as they are the easiest to get set up on, survive, and thrive, assuming they all have planets we can colonize, which would typically be considered overly optimistic, though I disagree and we'll discuss that later. But keeping in mind that ships probably are moving through space at 5 to 20% of light speed to reach these new worlds, then one 20 light years away is taking you 100 to 400 years to reach. It would likely take several more centuries to get that place vaguely comfortably habitable, and several more before their numbers had grown enough to consider sending out their own ships. Generally speaking, in our region of the galaxy, stars average about 1 per 35 cubic light years, or 1 in the cube just over 3 light years on each side. If we imagine a starship could move up to 100 light years in a voyage, a trip of 500 to 2,000 years at 20% to 5% of light speed, that would be a volume of 4.3 million cubic light years containing around 120,000 stars. If only 0.02% of those are our low-hanging fruit systems, that's only 24 star systems, while the more robust 2% figure for low-hanging fruit makes that 2,400 prime systems. Either is typically better than more classic space opera figures of galaxy-spanning empires having around a few million planets, since that implies about 1 in 100,000 systems is low-hanging fruit for settlement, or 0.0001%.
Percolation Theory.
To colonize out from those first star systems to others, we tend to assume Earth colonizes all within its reach, and that future systems do likewise, in expansion spheres. So Earth perhaps gets the first 100 light years around it in an inner sphere, then those systems get the next sphere out to 200 light years, then another spherical shell from 200-300 light years makes up the third sphere of expansion, and so on. This will eventually flatten to be more cylinder than disk-like as we approach the galactic scale, since our galaxy is more disk-shaped than spherical. It is also overly simplified, as these habitable planets are not uniformly distributed in direction or distance, and will not send out colonies of their own at some predetermined time. Indeed, many might never do it, while some settlements might fail entirely, as contemplated in the Aurora Effect and Pancosmorio theory. See those episodes for details, but the short form is that trying to settle a dead planet 100 light years from home and centuries of travel away is not an easy task, and we have no idea how hard it will be. This is where discussions of predictive models tend to bring up percolation theory, which is, generally speaking, a mathematical framework used in statistical physics and mathematics to study the behavior of connected clusters in a random graph. is used to understand the spread and flow of substances through porous material, much like pouring water through coffee grounds and through a filter, but also for the behavior of polymers, the spread of diseases, and you would have seen it in action with COVID-19 infection modeling maps. When it comes to stellar colonization, the spreading thing is humanity, and the idea of percolation theory can be metaphorically extended to model and analyze the spread of civilization across the stars. We won't dip into the math here and merely say that it tends to be better for predicting colonization rates when the journey is long and hard, many targets aren't considered viable, and where there is a rate of failure and a critical threshold to send out another colony from a developed system. While it still tends to produce the mostly spherical blob of settled systems, it isn't always going to, for different success criteria, especially as stars tend to come in clumps and clusters, not evenly spread, and the results can be counterintuitive for some criteria too. It is also helpful for considering the viability of interstellar trade, or conquest for that matter.
Backfilling systems.
Now, the low-hanging fruit approach and percolating out to viable stars isn't a bad one, but the usual notion on the show is that while you race for the nearest good systems, you will start backfilling those 98% to 99.8% of systems, or subprime systems, that did not qualify as prime systems once you get those nearby prime systems colonized. This might be done by your homeworld, or it might be done by settled systems, who want to fill up those empty stars right around them. Basically, you spread out in a thin web, and those nodes and corridors widen until you get everything settled, including less optimal systems. This may be only partial if it's considered too challenging to get some systems, or if you get them all, but a lot of times it's just a handful of outposts in a system for strategic purposes, and they never grow much on their own. This is also how we would generally expect solar systems to get settled, where the prime colonization targets get people first, and the system fills out till everything worth settling is settled, and probably many other places not worth settling out of stubbornness or strategic concerns. The reason we tend to think of it as backfilling, though, is because a star system on the edge of settled space still has prime empty systems to go after, while those less desirable adjacent systems, or even those closer to the ionosphere than that system was, might wait till the new frontier had been pushed out. At that point, some star system bordering you with only a tiny red dwarf, which is what most star systems have, might become more appealing because of strategic concerns about someone else settling it instead.
Closest available system.
While more valuable star systems should tend to get colonized first, and often you would want to colonize neighboring subprime systems, there's also a good case that the best system to colonize is the closest one available. Doubtless, if you have a subprime star 6 light-years away and a prime star 7 light-years away, folks will go for that better but slightly more distant star first. But the other problem is what makes a given star system prime or subprime. We tend to assume that it's always easier to build a rotating space habitat out of some asteroid in your current star system than to go to another star system and terraform a planet, and those you will usually be absorbing sunlight to run electric generation for the habitat, or bouncing it through filters to get the desired spectrum and concentration. We tend to assume Earth will send out colonists, but that for every Ark ship it builds, it will build several O'Neill cylinders, maybe several hundred, for use locally. Such being the case, you eventually end up with a lot of your population in space. And generally speaking, these folks are likely to be your better settler recruitment pool, since they are already used to living in a rotating habitat and working and living in space in general, from which it is reasonable to suggest that most interstellar colonists are already spacers, and certainly will be by the time they arrive. Thus, a planet around a yellow sun is less of a big deal to them, whereas some red dwarf with a thick asteroid belt orbiting it might look like the proverbial land of milk and honey and worthy of joining an Exodus fleet to reach. So too, in whatever passes for the currency to buy planets or star systems with, be it money, military might, diplomatic influence, or lottery odds, those vastly more common subprime systems are going to be way cheaper to get your hands on. They are also way cheaper to actually reach, since while the cost of a mission is not directly related to distance, it still goes up with distance, and more sharply with speed, which can be decreased if you're closer and don't have to travel as fast to get there and don't have to race to reach it because there's not as big a battle to see who gets to claim the system. And if I can launch 10 colony missions to 10 subprime systems 5 to 10 light years away for the same cost as reaching the nearest single free prime system, maybe 20 light years away, that might be a better investment.
Colonizing.
Of course, all this talk of colonizing prime or subprime star systems assumes people are even colonizing entire star systems with single expeditions, and those expeditions can usefully travel between star systems in single jumps. We don't have ships that move that fast yet, and while we do have decent designs, like the Orion Drive, we don't really know if that would turn out economical compared to sending slower ships, even if we have fusion engines or beaming systems. Space is huge, and we may find the only economically viable way to colonize it is to move out at a crawl at 100th or even 1,000th of light speed. And of course, if you do have viable power supplies for engines able to achieve that speed, you still have power supplies viable for running life support for thousands of astronomical units from home, where the sun appears as merely one more bright star in the sky. Indeed, if you are curious, while our sun is brighter than most stars, we could only see it at about 50 to 60 light years away, and that in optimal viewing conditions, which space is, no air or weather in the way. But even just at our nearest neighboring system, our sun would still be a fairly mundane star in that sky. Alternatively, even out at Pluto, it is still vastly brighter than the full moon is. Even out that far, we can potentially still use solar power by using very large, thin parabolic dishes to concentrate light. After all, you might need a square kilometer of metal foil to collect a megawatt of power out there, but how much does that metal foil really cost? How many days of power production to run the smelters and rollers to make it? Not very much at all, and automation changes many equations. So too, even if we never got fusion working, we know how to make breeder reactors, and that means every kilogram of thorium and uranium represents about a month worth of living on our general concept of a human needing about 1 trillion joules a year to run all their life support and hydroponics. And that assumes a lot of leeway and a fairly luxurious lifestyle too. We discussed pushing that envelope further in our Cyborg Civilizations episode from last week. 1 ton of uranium or thorium should supply an entire family for their whole life if they were being conservative with its use, and we should be able to rely on several trillion tons being readily available in the solar system to mine on planetary crusts, moons, or asteroids. You can also be sending power out in beams from huge solar collectors in-system. This means that even if we never find a way to practically move at greater than 1% of light speed, we can slowly make our way out from Earth into deep space, even setting up a robust civilization in the Kuiper Belt. Even if we never make fusion work, and if we do, we can make power plants that function to lavishly produce life support energies in the Oort cloud much more easily than ships moving at 10% of light speed. I think we can and will achieve the latter too, but the key thing is that we do not have to. We can employ the colonizing approach of just slowly moving out from our planet at 1% or even 0.1% of light speed, settling every rock more than a few kilometers across, and creating space habitats to tow into place where we need a way station but no rock is available. If you employ colonizing though, it means you settle and make a home on every star. You never skip any star, subprime or not, because you never skip any object bigger than a house. Stars become the verdant river valleys of civilization, but you don't have to have them as archipelagos surrounded by emptiness, because even in the deep void of interstellar space, there are places you could make a home. There may be 1 trillion or more icy bodies a kilometer across or larger in the Oort cloud, and every single one of those could run a fusion reactor for untold millennia to support a homestead or village habitat of dozens or even thousands. Even in the small case, that totals thousands of times Earth's current population living in the empty void far from the sun. Tiny compared to the Kardashev-scale civilizations in the sunnier regions perhaps, but still immense, and enough to act as humanity's hand reaching ever deeper into space till it encounters another brighter star. And on galactic timelines, if your civilization can only move at 0.1% of light speed and only extends its borders at 1/10 of that rate overall, it still means you reach the galaxy's edge 100,000 light-years away in a mere billion years, not even 1/10 the time this galaxy has been around, or 1,000th its remaining lifetime.
Gardner chains and cones.
Of course, it would be nice to settle the galaxy in less than 1 billion years, and it should be viable in under 1 million, and Gardner fleets are a good approach to doing this. They come across some new system and stop, or perhaps drop a splinter fleet that stops while they go on. Normally we assume they stop and drop off colonists and help them get set up while taking on new raw materials to be processed into new terraforming and colonial gear during the next leg of their journey, and excess gets used to build more ships. As they go, they are creating a chain of worlds behind them that have a common and shared origin and can send along assistance, and along which crew or colonists who want to leave the trip can go backwards to some earlier point in that chain, even all the way back to Earth. They may be biologically immortal or do the trip on ice. Then as they fly along building equipment, they also breed and train more people, and as they fly ever further from Earth, they break up the fleet, build more ships, break up those fleets, and you get something more like an expansion arc or cone. So you might send out one such fleet from Earth to each of the zodiac constellations, and instead of getting a dozen long lines out to the galactic edge, you get expanding cones covering the galaxy, as an example. If we assume these were able to do a bit better than 10% of light speed, and effectively did that after including their layovers, you would get the whole galaxy settled in around 1 million years, and some pieces reaching the galactic rim in just 250,000 years. We chronicle the flight of one of those Gardner fleets in our Life in an Interstellar Colony series, which begins with a trip to Saturn and ends with a fleet departing for intergalactic colonization from the Terminus system at the galaxy's edge.
Automated Vanguard.
Of course, that colonization goes a lot faster if you have Vanguard elements arriving ahead of you to build pushing beam arrays, assembling power collectors, starting mines and refineries, or even just doing flybys to give you accurate advanced readings on that system that even a planet-sized telescope could not achieve light years away, which you might have built too, see our Mega Telescopes episode. These do not have to be automated, but it seems a more practical approach at a lot of levels, and in this context we usually do not mean an AI smart enough to qualify as a person. You can take this a lot further though, and unleash a wave of self-replicating robots, but they are not superhumanly smart, just barely smart enough to do the job. That job might be exploring systems, or setting up pushing beam arrays and transmitters, or they might be terraforming planets as they go for us to later settle behind them. Indeed, it might be building entire Dyson swarms worth of habitats around every star in the galaxy awaiting human colonists. For that matter, a good seed ship could not only build the habitats and grow plants in them, but even grow animals and humans, and potentially raise them itself to be regular old people, as opposed to axe-crazy, socially maladjusted folks who even the kids from Lord of the Flies might get nervous around. If you pursue this route, you presumably have thoroughly tested your automated growth tanks, child-raising androids, and AI back here before launch. One caveat though, this approach often tends to assume folks are either very lazy, and thus careless, or are in a hurry to get into space, on the idea that they want to claim all of it for themselves. So it is worth noting that the problem with space travel is that you cannot outrun or evade pursuit if you plan to stop somewhere. If you're using onboard fuel to slow down, then an equal device that's chasing you can burn that fuel to outrun you and ram you. They don't need to slow down, nor do they need to be as big, and you are easy to track by your drive system and have to turn it visibly on to change directions. Even using the tactics for free slowdown does not evade this, because your extra mass for that mag sail or solar sail daisy chain is mass they did not have to spend, and can use for something else, like more engines and fuel, or guns and missiles. Thus, folks colonizing space either do it semi-cooperatively, which might be friendly, or more Cold War-ish, or nobody gets to do it at all because their ships get blown up by enemies until you stop sending them or stop having enemies. Which means you're not in a rush to colonize anymore. Tactically speaking, you wouldn't be either, as sending off multi-century voyages that will likely need millennia to return you a useful profit, albeit an enormous one when it does pay off, is not a good use of resources in the middle of a war. In all those cases, you have a lot of time and motivation to get your programming and techniques thoroughly tested and proved before inflicting a hegemonizing swarm on the galaxy.
Central Collection.
Of course, if you are trying to win a war back home or prevent colonies arising and causing problems, it may make sense to send automated ships out to gather resources and bring them home instead. You will need to put several million solar masses in our solar system to make it too dense to safely dwell in, and at that point, you need to widen your zone linear to your mass increase. But you could cram most of the galaxy's mass into an area no bigger than our local interstellar neighborhood if you really wanted to and were careful in your placement. Indeed, this is how you build a Borch planet, which has trillions to quadrillions of times more living area than Earth has. So stockpiling hordes of raw materials and fusion fuel to keep your civilization running for half of eternity is a viable option. This also works if you're a singular intelligence like an AI Jupiter brain, Matryoshka brain, or some other megamind several orders of magnitude bigger. Even a whole galaxy crammed down needs to be under a light year in radius to be a black hole. But again, that event horizon radius rises linear with mass, so you start chasing a faster moving goalpost if you try to collect beyond your own galaxy.
FTL and Multiverse Strategies.
You can potentially be colonizing other galaxies too, and dragging them back if you want and are very patient for use at home, or even your whole supercluster. But beyond about 10 billion light years, it gets real dubious if you could ever hope to reach that spot before time and Hubble shift kept you from ever arriving, or doing so after it has been claimed by entropy, or simply by some other species that arose there in the tens of billions of years you spent traveling there. Introducing FTL to this equation makes you reaching those further away places more viable, and all the tricks we saw today can be adapted to FTL. If your warp or hyperspace travel lets you move 1,000 times light speed, then a voyage to our closest neighboring large galaxy, Andromeda, 2 million light years away, still takes 2,000 years, and you still need to use a generation ship, or maybe use the Gardner ship approach here too on its way to other galaxies. As we noted in intergalactic colonization, there's a lot of stars forming a loose bridge between our galaxies that you could use as waypoints too. Folks popping through wormholes might not spread very spherically, and much like our notions of slowing down around distant black holes or flying through red giants to slow ships sent out at very high speed, these could become new nodes for civilization to percolate out from. Only in the wormhole's case, it might be a new node halfway across the universe, or even in a different universe. In Stargate Universe, the sadly short-lived third installment of that great franchise, the show takes place on a seed ship that's flying through galaxies, dropping off stargates on various worlds, then after some centuries or millennia, moving to the next galaxy, a process it and its companion vessels had been at for 50 million years, give or take. We can also imagine colonizing not just over the edge of our cosmological horizon or the observable universe, but even other universes or the multiverse, which may have more empty copies of Earth waiting for us to colonize than there are grains of sand in our whole universe. And here we might see the same prime versus subprime and backfilling approaches used. We never know if we might find ways to move beyond the bounds of science or the edge of reality itself.
Early settlement.
This episode is not just about the trip there, but also what to do once you arrive. And while we won't be dipping too much in terraforming today or building megastructures, we do have episodes on that, and we'll be looking at life as a planetary governor next month to contemplate how to handle some of these problems. Today, for the sake of brevity, in an episode already as long as a movie, we're mostly going to be bringing up those initial considerations and problems for once you arrive. And one of those first ones is the change in power between your spaceship's captain or fleet admiral to the planetary or system governor. Indeed, this is another reason I like Gardner fleets as an extension of generation ships, because you are bound to have had such problems pop up in that flight and factions form, the kind sleeper ships or FTL vessels wouldn't have as badly, but a century is a long time for schisms to form. Being able to shuffle folks to different ships, which you can do during the flight, or break up your fleet or disperse colonists to multiple landing sites are some of your options for dealing with that. So is encouraging bored folks or malcontents to go on ice for the journey or threatening to put them on ice and ship them back to Earth.
Planets versus moons.
This takes us to our first consideration though, and that's that you don't need to be treating an entire solar system like it was a small outpost in a small corner of a planet, as we often see in science fiction. That means you do not have to put everyone down on one landing site, and moreover, you don't need to put them all down a big gravity well. Strictly speaking, as we discussed in our series, Life in a Space Colony, the icy moons of some gas giant like Jupiter or Saturn are much better places to park your ship early on. Your crew is already used to living in a space habitat. Some might even find a planet surface rather scary compared to a habitation drum. Here you can get all the raw materials you need to make more of them and ships too, and fuel and propellant for those, without needing to go further down a big gravity well, including closer to that star. Also, if you're planning to terraform a planet, odds are good you'll want to bring in your heavy guns first. Terraforming is not like spray painting a desert green. You could bombard the place with nukes and leave the landscape less impacted than you will when you start dropping billions of tons of ice down to form oceans or put nitrogen and oxygen in the air, or unfurling continent-sized orbital mirrors or shades to alter temperature, followed by all the endless mudslides, sinkholes, hurricanes of mud, and possibly setting the atmosphere on fire. So, limiting yourself to some domed ground bases and orbital habitats, while growing your main population in bases on various asteroids and moons, might be a wiser idea.
Aurora Effect.
This is all assuming there's no life already present on that planet, and that's what happens in Kim Stanley Robinson's novel Aurora when some colonists reach a planet and find it's got life that's decidedly unhealthy for them. They end up giving up and going home, and that's understandable if you find you've got native life on some planet. Let it be and settle elsewhere. We examine that more in our episode The Ethics of Terraforming, and we examine the Aurora Effect in its own episode, and the parallel idea of pancosmorial theory in its own episode too. But we can't discuss colonization without acknowledging that it is very hard and full of possible ethical challenges, even if there's no alien life in play. You could easily fail doing the classic science fiction approach of just landing a few thousand colonists on some Earth analog planet 100 trillion miles from help and a century from rescue. But we're not talking science fiction, even if it helped us imagine many of the challenges we'll face. Technology does offer solutions. And for instance, if you need rescue, you just go on ice in space for a century till they come and get you. Or on top of a mountaintop above the biosphere of the alien planet if you landed on some death world full of mega murder raptors and ultra plagues. You also wouldn't be walking around in such a place like some naive and unarmed teenager in a horror film waiting to get murdered. You might be an augmented cyborg walking around in a suit Iron Man would envy with a bunch of killamajig mortar drones hovering around you, supported by orbital ships and defense platforms that can launch precision orbital strikes. Technology and automation let us solve problems. So does time. One upside to journeys that long, especially if you've been wisely sending flyby probes and advanced automated scouts, is that you should have a good idea what you're getting into and can run simulations. And not just modeling, but virtual reality drills or holodeck scenarios. You also have parallel missions going on to other systems and help from back home, all feeding you suggestions from their own experience and ruminations. There's time lag for communication, but you can get help and reinforcements, and you have time.
Orbital Infrastructure.
You also want to focus initially on getting your orbital infrastructure and general system space infrastructure set up. You can refuel, restock on raw materials, send the other colonists on to their next stop, send the folks who want to go home back home. You build a bunch of solar collectors to power the sorts of engines you need to forge new worlds, to transmit large amounts of data back home, and to slow down fleets coming in to bring you help, which can also provide defense from interlopers arriving to attack you. You don't land ships on the destination planet, you build orbital rings or space towers to let you move gigatons of gear down and up. You create an entire detection, positioning, and communication grid on that planet, Starlink from day zero, and you build orbital habitats there and in any promising asteroid or moon that looks like a good and easy supply of the resources you need. You went to all the effort to become a spacefaring species, You do not need to abandon that by landing everyone on some godforsaken planet while you try to hammer life into it. It is much easier to build some smaller cylinder habitats and get them livable than to try to make a whole planet livable. So dream big, dream awesome paradise planet, but start small and get everything in place to let you do it right. And a lot of your folks might not even want to be on that planet, especially a lot of people who were born and raised in the habitation drum of an interstellar Ark ship. To them, cylinder or ring habitats are the normal way to live.
Getting neighbors.
So you're not a lone planet from the outset, you have neighboring colonies from soon after arrival, but that might not be the end of it. There are 1 million minor planets in this solar system of ours, each able to house a decent-sized city or even larger nations. Our planet is home to billions who all have to learn to play nice, and they begin the modern era with a lot of baggage of less friendly times. Such being the case, there is precious little reason why some colony Ark of a few thousand, or even a few million, would ever expect to be able to claim a whole planet to themselves, let alone a whole star system. This is even more so in the context of colonizing or backfilling colonization, since folks are planning to settle every rock in a system and in between too. If some big nation or corporation or group sent you there to claim the place, they probably would like to send more follow-ups and immigrants, and likely said so from the outset. You probably got offered first place with added effort and risk in exchange for first dibs on choice spots, not the whole system. If you came on your own, then do not expect folks back in more civilized space to side with you when other ships show up looking to settle empty continents or other planets. They'll probably just view you as selfish or xenophobic and not feel much urge to take your side. Of course, they might be sending invasion fleets too. A few centuries of change back home can make for big differences in behavior from your fellow humans, and indeed they might all be cyborgs, post-humans, or AI at that point. As I said near the beginning, interstellar colonization is not your go-to for solving population growth issues. Even shipping someone on ice, on a sleeper ship, moving just 1% of light speed and propelled by a beaming array, is still taking at least a quadrillion joules of energy, which by our earlier estimate of 1 trillion joules a year per person equals 1,000 years of life support. Nonetheless, it is an option that can help with the problem, especially in early Kardashev 2 years where energy is way more abundant than people, and one way to maintain that sort of abundance is to cap your population at a point where you still have it, and shipping extra people out in ships to new systems. After all, a quadrillion joules is just a few trillionths of the sun's output every second, or the energy contained in just 1 kilogram of fusion fuel, such as a jug of water.
Solar economy.
The immense amount of energy being radiated by our sun is a reminder that in the longer term, your colonization aim is a complete solar economy, one able to wield that huge solar output, which even for the dimmest red dwarfs is enough to support a quadrillion people in comfort. You may settle all those planets and minor planets, and still go on to build megastructures that dwarf them in scale. You can also be paying back the investment in your original colony even at a high interest rate with relative ease. They gave you a gigaton of processed metals they built into a ship for you, 100 times that in propellant, and 1 trillion joules of energy to get you there, all taken from asteroids that have been drifting in space for 1 billion years and a star wasting sunlight into the empty void for just as long. It might take you 1,000 years to send home repayment, but you can send them back 1,000 times what they invested in you and barely notice it once you're developed as a system.
Sending out new arks.
And making good on those debts is not a bad idea as you get big enough to consider sending out your own colony ships to other worlds, to be a good role model for them to do likewise down the road. Reputation is also probably a valuable commodity in long-lived and high-tech civilizations, and purchased cheaply with that repayment. Those new colonists might have to journey a long way to find an empty system too, as odds are good more colonies further from Earth have been settling past you while you grew big enough to contemplate sending your own. Ultimately, we'll never know if space colonization is truly viable until we not only have several established colonies, but those in turn have sent off their own colony ships, as it shows it is a self-perpetuating process, not reliant on Earth to keep it going as the frontier moves beyond us. Though indeed Earth could keep settling arbitrarily far from ourselves, especially if we had early colonies agreeing to send some resources back to be used to build more arks from, or to replenish what we used to build them. Those more distant efforts would use different strategies than nearer ones, such as those we imagine for crossing a whole galaxy or fleeing pursuit. So too would those further missions sent further in the future, as we learned more about successful interstellar travel and settlement and developed more general technology, and as Earth will likely always have the most advanced technology and greatest collection of knowledge and resources, it may be the place sending out most colony ships for a long time. Folks may jump on board from colonies along the way, boarding from lighter shuttles matching speed, or other ships built locally planning to join the colonial fleet. Indeed, many of the folks from Earth might get off before the frontier, settling on developed planets along the way that were as pioneer-esque as they wanted, and giving their seat up to someone from that planet. There are a million ways interstellar colonization might proceed, a million different tales to be told on each of the millions of ships we may one day send out to spread humanity across the galaxy. Some hopeful and humorous, some touching or tragic. But for today at least, our story is complete. As I mentioned earlier, this episode is a collection of ideas developed over many years as new ideas have been gathered and discussed both here on the show's various social media forums and elsewhere. This show turns 10 years old in 2 months, and we could not have gotten there without a brilliant audience and some amazing partners, and one of those is Brilliant.org, our longest-running sponsor and the creators of an amazing and ever-growing catalog of lessons on math, science, data, probability, computers, and AI. Maybe you're thinking of a career in STEM or even space. Maybe you just want to learn some more for fun, and whether you're a beginner or advanced, Brilliant can help. They let you build real knowledge in minutes a day, with fun lessons you can do whenever you have the time. Learn through problem solving and doing, with hands-on interactive content that's fun, immersive, effective, and intuitive. Brilliant's been a great partner to this show, and they can be a great partner in your own journey, whether it's career development or just a desire to learn. You can try everything Brilliant has to offer for free for a full 30 days. Just visit brilliant.org/IsaacArthur or click on the link in the description. You also get 20% off an annual premium subscription. This episode took a lot of time to produce, and we tried to be comprehensive, but even after over 2 hours, there was so much about space colonization we had to skim or skip, and many of the topics are covered in greater detail in their own episodes. One thing we didn't discuss today was why we are expecting to have a galaxy worth of stars to colonize all to ourselves, rather than running into alien civilizations everywhere. The galaxy seems to be empty of them as best we can tell, and one notion for why is that ancient empires may indeed have arisen but chosen, or been forced, to go to sleep, and we'll examine the idea of ancient dormant alien empires on July 14th. Then we'll ask if maybe the conditions in this universe might be uniquely suited to life arising, as we contemplate the idea of the fine-tuned universe and what its implications would be if true, especially for the Fermi paradox. Then we'll discuss the topic of machines that can self-repair on the 25th. If you'd like to get alerts when those and other episodes come out, make sure to hit the like, subscribe, and notification buttons. You can also help support the show by becoming a member here on YouTube or Patreon, or check out other ways to help at isaacarthur.net. You can also catch all of SFIA's episodes early and ad-free on our streaming service, Nebula, along with hours of bonus content like Planetary Archives and Stasis Vaults at go.nebula.tv/isaacarthur. As always, thanks for watching and have a great week.